In the last video, we built the hardware for a flags register, which we can use to track certain conditions, like whether the result of an operation is 0, that's what the 0 flag is for, or whether an operation generated a carry out of this last bit into the carry flag. For example, if we add two numbers and the result is more than fits in 8 bits, then we'd want to set the carry flag. We also hooked up a control line to control exactly when we load a new value into our flags register, and that's this flags in signal down here, which is part of our control word. We also hooked up the output, or really the current state of the flags register. We hooked that around into two additional address lines of our microcode EPROMs. That way, what's going on in the flags register can influence the control signals that are coming out of the EPROMs, so we can create instructions that work differently depending on what's going on with our flags. So let's actually create some instructions that use the flags register. Now this is the microcode that's currently programmed in the EPROMs. And remember, the EPROMs are really just a big lookup table. You've got some address lines going in, and depending on whatever those address lines are set to, you've got some particular output that comes out. So for example, if we look at our add command for this particular step, we're saying if the instruction is 0010 and the step is 010, then this is the control word we get. And you can see these three address lines here are the step. They're coming down from the step counter over here. And then these next four address lines are the instruction, and you can see that coming from the instruction register. And so if all of those are set like this, then we want this control word. Of course, this control word is 16 bits, so we've got two EPROMs, and I'm using the 8th address line to tell one EPROM, give me these 8 bits, and tell the other EPROM, give me these 8 bits. Well, it used to be 7 bits before we added the flags register. And you can see that 8th address line here. It's just hardwired low on this EPROM and high on this other EPROM. And that just lets us program both EPROMs identically. So now we're adding two more address lines for our flags. And that's going to change what our lookup table needs to look like. So here's a copy of that lookup table where I've added the carry flag and the 0 flag now, because our control word is now going to depend on the instruction, the step, and the flags. Now, in most cases, you see the flags don't matter. And we want to do the same thing regardless of whether the flags are set or not. In fact, all of the instructions we've got so far are like that because we haven't had these flags until now. But I've added two new instructions, jump on carry and jump on 0, here that do make use of the flags. So jump on carry for step 2, 010, if the carry flag is not set, then none of the control signals are set. We don't want to do anything. But for jump on carry step 2, if the carry flag is set, then this is the control word. We're doing instruction register out and jump. And this is the same thing as just the normal jump instruction. And of course that makes sense that the jump on carry instruction would do what a normal jump instruction does, only when the carry flag is set. Then for steps 3 and 4, regardless of what the flags are set to, we do nothing. And that's just because we don't need to do anything else for a jump in any case. Jump on 0 works the same way, except in this case, whether we do the jump or not depends on the 0 flag rather than the carry flag. There's one other change I made here, which is I added this last column here for the new flags in signal. Before this extra bit wasn't used and it was always just 0. But now I want to have it set during the last step of the add and subtract instructions. Because it's at this point when we've just done our addition or subtraction, and we're taking the result and putting it back in the A register, we also want to update the flags register to match whether that result was 0 or had a carry. Now in all these situations where we don't care what the carry flag or 0 flag are, all of these X's here, it means we need to have the same thing programmed in the EPROMs in each of the different possible combinations. So that means we're going to be using a lot more of the EPROM memory. In other words, if we look at how this information is mapped to memory addresses in the EPROMs, it looks something like this right now. So A0 through A2 tell us which step of the instruction cycle we're on. The next 4 bits, A3, A4, A5, and A6, are the opcode of whatever instruction we're executing, and that comes right from the instruction register. And then A7 is this address line I'm calling byte select, which tells us which 8 bits of the control word we're getting out. If it's a 0, then we're getting the first 8 bits. And if it's a 1, then we're getting the last 8 bits of the control word. That's why to get 16 bits at the same time, we've got 2 of these EPROMs, and they're programmed identically. And then A7 is just 0 here, and it's 1 here. They're just hardwired. So that's what's programmed there now. We've got all the opcodes, 0 through 15, and then for each of those opcodes, we've got the steps, 0 through 7. And that's for the first half of the control word, and then we just repeat that again for the second half of the control word. And so that goes from address 0, all zeros here, up to address 255. We've got 8 ones here. But now we also need to handle all the combinations of the carry flag and the 0 flag. So that actually means we need 4 copies of this. The one we've got, one with the carry flag set, one with the 0 flag set, and then one with both flags set. And for the most part, these 4 copies will be pretty much identical because for the most part, the control word it really doesn't depend on the flags. But there are these 2 places where we do want it to depend on the flags, here and here, and this will let us do that. Now you might say it's maybe inefficient to take up 4 times as much memory in the EPROMs just to handle these 2 little one-off cases. And fair enough, if you want to minimize the size of the EPROMs that you need, then this might not be the solution for you. There's probably other solutions that you could come up with that would be better to achieve that goal. But that's the deal with engineering. You're always making trade-offs. It's virtually impossible to come up with a perfect design that's going to optimize every variable, especially when you consider that the cost of the time that you spend cooking up that perfect solution is also something that you probably want to minimize. But my goal for this is really just to be flexible enough to tinker with and easy enough to understand, and hopefully I've done okay on that. Okay, so now let's take a look at actually programming these EPROMs. So I'm going to use this Arduino-based EPROM programmer that I came up with in a previous video. So if you're unfamiliar with what this is or how it works, check out that other video. Here's the code from before, and I'll start by making a copy so we can hang on to the previous version. That way it'll be easier to find the code for anyone watching those previous videos. And the first thing I can do is pretty straightforward. Remember we added another control signal to the control word for loading the flags register. So I can define that flags in signal as using that final bit of the control word. And then we're using that flags in signal here on step 2 of the add and subtract instructions. And so we can just add fi to that step of add and subtract. And now I've got to fix up all the spacing. I'm sure it's not going to work right if everything doesn't line up perfectly. There we go. Now I've got this nice representation of our microcode here. But like I was talking about before, we basically need 4 copies of this, slightly tweaked. Now I could just copy and paste in this array, just these 16 lines here, 4 times, and just end up with a big long list of 64 lines that, repeats mostly the same thing. But, I worry that that's just kind of asking for trouble. If the 4 copies get out of sync in some subtle way by accident, that'll be a real pain to chase down what's going wrong. So instead, what I'm going to do is use what I've got as kind of a template and have the program make 4 copies of it. That way we can explicitly make just the few tweaks that we want to each of the 4 copies and know that the rest will be the same. So what I'll do is define an array of arrays to hold all 4 copies. And then what I'll do is I'll rename this data array here to make it clear that it's the template. And then I'll define a function to initialize that microcode array. And basically what I want to do is just copy that template into the microcode array 4 times. And so this is taking this template that I have here, this microcode template, and just making 4 copies of it in these 4 spots in this microcode array. And the first copy is for when the 0 flag and the carry flag are both cleared. Next is for when the carry flag is set. Then for when the 0 flag is set. And finally for when both the 0 flag and the carry flag are set. And I'm also going to change the way that this array is defined to be a little bit more structured. So rather than being just kind of a flat array of I think it's 128 control words is what this works out to be, rather than just being kind of flat array of 28 control words, what I want to do is change that to be an array of 16 instructions, and then each of those instructions will be an array of 8 control words. So it's going to look pretty much the same, but what I'm going to do is each of these instructions will be an array of 8 control words, and then the overall template will be 16 of those instructions. So I'll go ahead and just add all these extra braces here, and you'll see why I'm doing this here in a minute. Basically, it's just going to make it easier to get at a particular value if we know the instruction in the step. And then another sort of cosmetic thing I'll do is just define some constants here to make it more clear what the different combinations of flags are. And so this is just the different values of the flags. Then I can come down here and replace these sort of 0, 1, 2, 3 with those constants to make this a little bit more clear. And I think that makes it just a little more explicit what's going on with the microcode array. And I know I've already got comments here, but I like making the code itself as self-explanatory as possible, since I've found that comments don't always tend to stay up to date, and there's nothing that enforces that the comments are correct. So now, of course, we've got to go and call this initialization function. So I'll go ahead and do that down here at our sort of entry point here in setup. So just when we start off, we'll call that function. And then for the actual programming here, where we're programming the EPROM, since we've changed around the data structures so much, I think it's probably going to be easiest to replace most of this code that's writing to the EPROMs. So what I'm going to do is, rather than splitting this up into the 2 loops here, for the 8 high order bits and then the 8 low order bits, I'm just going to collapse this into one loop that goes through the whole address range. So I'll get rid of one of these loops. And so the whole process from when we start programming the EPROM to when we're done will just be this one loop. And so if we're going through the whole address range, if we go and look at how our EEPROM memory is laid out, we want to go from where all the bits are 0, so from address 0, all the way through all of these up until we get to where all of the bits are 1s. And so we've got 10 bits. 10 bits of 1s is 1023. We can also check that by doing 2 to the power of 10, because we've got 10 bits, and that's 1024. So there's 1024 combinations that you can get with 10 bits. So we'll loop our address from address 0 up into 1024. Okay, so when we get to that address, when we write to the EEPROM at that address, what is it that we want to write? Well, we want to write that microcode value that we generated here when we initialized things. And so that microcode, go back up here where we define that, it's an array with 4 values in it. So the first index into that array is going to be the flags. Then the next index into it is going to be, well, into the template that we copied in. And so actually, maybe what would make sense is, since this template is an array of 16 instructions, each with 8 steps, I could make the microcode an array of 4 flags values, each with 16 instructions, each of those instructions with 8 steps. So we've got flags, instruction, and then step. So when we're writing that out to the EEPROM, we're writing to each address in turn from our microcode the correct value for a particular flags value, a particular instruction, and then a particular step. But how do we figure out what this flags value, this instruction value, or this step value ought to be? Well, we should be able to figure that out from the address. Well, we're in this loop that's going through all of our addresses from 0 all the way up to 1023. So we're going through every possible value of address, and our address is broken up, by bits. So if we look at just 3 bits of that address value, we can figure out what step we're on. If we look at just these 4 bits, we can figure out what opcode we're on. If we look at just these 2 bits, we can figure out what flags we're on. So what we want to do is, when we get into this loop, we want to look at this address, and from that address, we ought to be able to compute what flags value we're at, what instruction we're at, and what step we're at. So the flags, that's going to be the first 2 bits of the address. So we're looping through this whole thing, and then we're going to start at 0, 1, 2, 3, 4, 5 as we loop through our addresses, and we just want to look at the first 2 bits. So to look at the first 2 bits, what we can do is we can do a shift right operation. So we have 10 bits here. If we shift all of this to the right by 8 bits, then the only 2 bits that we'll have left are the first 2 bits over here. They'll be shifted all the way to the right, and everything else will be 0. And so those 2 bits that we've shifted will be our flag bits. So we can take, to sort of figure out our flags, we can take address and shift right 8 bits. So that's flags, and so that'll get the right flags value for this particular address. How about instruction? Well, instruction is our opcode here. And so opcode is these 4 bits, and we could do the same thing. We could shift right, well, in this case, 3 spaces, and that would get our opcode over here to the right, and then the value of those 4 bits then would be the opcode. But we might have some other stuff over here. We might have our byte select, we might have our flags. What we can do is we can use a bit mask to just pick out those 4 bits before we shift them over. So here's what I'm talking about. So if we take our address and we AND it with a binary value of 000111100, basically what we're saying is, if there's any bits in our address in any of these places that are zeros, since we're ANDing it with a 0, we're going to get a 0 no matter what. If there's any bits in this address that are either a 0 or a 1, we're going to get that same 0 or 1 when we AND it with a 1. And so what this is going to effectively do is, if you take an address, any value anywhere in here, and you AND it with that binary value, what it's going to do is it's going to 0 out everything but the opcode. So once we've zeroed that out, what we can do is we can shift that to the right, and then we'll be left with just the opcode as a number from 0 to 15. So if we take this address ANDed by this bit mask, we can shift right by 3, and that'll give us our instruction as a number from 0 to 15 as to which instruction associated with that particular address. And then we can do the same thing with step. So step is going to be our address. And in this case, step is already shifted to the right. I mean, it's just these first 3 bits over here on the right. So we don't need to shift it anywhere, but we do need to kind of 0 out the rest of the bits. And so we can do the same thing with an AND. So we can AND this by all 0s and then 3 1s. And those 3 1s will preserve the last 3 bits of the address here and give us the step, and it'll 0 out the rest of that. Even if we get into here where not all of these bits are zeros, it'll still 0 them out, and we'll just have our step from 0 to 7. And so I can actually clean this up a little bit, make things kind of line up. And the other thing I could do is, actually with the flags, we're shifting this all the way to the right. But for consistency, what I can do is I can also say we're going to zero out all but those 2 bits. And that, again, it just sort of makes the code more readable. So if we say address and those first 2 bits, and then the rest are 0, and we shift right to the 8, that doesn't really do anything because when we shift right to the 8, we lose all these other bits anyway. But it does make it more consistent here. And you can see, okay, the flags are the first 2 bits, the instruction are these 4 bits, and the step are these last 3 bits. And that's, consistent with what we see here. But of course, we've forgotten one bit there, which is our byte select. And so that suggests that maybe there's something missing in our code here too. And in fact, there is. Because when we write our microcode value here, remember this microcode value is a 16-bit value. And the EEPROM's only going to look at the least significant 8 bits of that. And right now, because we're ignoring this byte select, we're going to be writing only these least significant 8 bits to every value, whether the byte select is set or not. So to fix that, first what we want to do is figure out, if we're on an address where the byte select is set. So we can do byte select equals, and it's going to be the same pattern here. And of course, it'll be this bit that we don't match yet. And so now you can see we're matching all of the bits. The first 2 bits are the flags. The next bit is the byte select. The next 4 bits are the instruction. The last 3 bits are the step. And here we want to shift right as well. The byte select is here. We want to shift that all the way to the right. So that's going to be 7 places to the right. And so now that we have our byte select, what we can do is, depending on whether the byte select is set or not. So if it's set, what does that mean? So byte select, you can see that's set here on the chip on the right. And so when that's set, we want to get these bits on the right here, which are the least significant bits. So if byte select is set, then what we want to do is write out the last 8 bits of our 16-bit word here. So if we actually just do what we're doing here, we're writing the value that we get from the microcode, this write EEPROM is only going to take 8 bits anyway. So it's just going to chop off the first 8 bits like this, and we're going to be left with what we want. So what we want to do is when byte select is not set, so the other case here, else, we want to do the same thing. We want to write to the EEPROM, but we don't want to write these 8 bits. We want to write the top 8 bits. And so what we need to do is we need to shift them over 8 places. So we shift right 8, and that'll shift all 16 of these bits over to the right here, and we'll lose these lower 8, and we'll just be left with the high 8 bits here, and that ought to give us what we want. And so I think this ought to program all 1024 bytes of our EEPROM correctly. And then we print done, and then we print the contents of the EEPROM. And actually, I think here when we print the contents, we're probably not printing enough to see everything that we programmed. Yeah, so if I find our print contents here, you can see we're going from 0 to 255, but maybe this should be 1024. But actually what I'll do is I'll just give it a length, and then we can pass that in. And in fact, we can give it a start point too. So this print contents will now take a start and a length and print however much we want. So here I'll just say start at address 0 and give us 1024 bytes. So that should print the whole thing. So let me try compiling this and see what mistakes I made. Okay, well that's supposed to be flags. You probably were all screaming at me when you saw me type that. And we're missing a semicolon. And it's compiled, but I'm getting this low memory available. And that's because the Arduino Nano has only got 2K of memory, which is not a lot. And we're using a lot with all of this data that we've now got in here for not only our template, but also all of the copies for the different flags values. And so this is just warning us that we're using a lot of that memory. Now the Arduino has got some different types of memory. So the Atmega 328P is the Arduino chip that we're using. And it's got 2K of SRAM, but it's got 32K of flash. And so if you've got data that you don't need to write to, you don't need to modify, it's just going to stay the same throughout the entire program, you can actually put that in this flash memory to free up some of this SRAM. And so in our case, we've got the template here, and we never modify the template. We modify this microcode, right, because we copy things from the template into it, and when we add some exceptions here, we're going to be changing some things in this microcode here, but we're never changing the template itself. So what we can do is we can actually put the template in flash, which is called program memory, rather than loading it into the SRAM when the program runs. And that'll save 16 times 8, and these are 16-bit values. So that would be 256 bytes, which is a decent chunk of this 1598 that we're using. So to put this into that flash memory, that program memory, you basically just preface this with const progmem for program memory, and that'll store this in that flash rather than loading that into the limited SRAM that we have of 2048 bytes. Although there's one big gotcha with this, which is if we're copying from program memory into SRAM, which we're doing here with this memcopy, you've got to use a special version of mcopy. So you've got to do mcopy_P to use the Arduino version of memcopy that will copy from program memory. So if we don't do that, we're going to find these memcopies don't actually work. So now let's verify this. And now it's compiled, and you see we're using less memory and we're not getting that warning anymore. And of course, I do need to add, the jump carry and the jump 0 instructions. That's the whole point of what we're doing here. But before I do that, what I'll do is just test out what I've got so far before we add anything more complex to it, and just to make sure I haven't broken anything yet. So I'll pull these EPROMs out so we can reprogram them. And then I want to put each one into the EPROM programmer here and hook the programmer up to my computer. All right, so what I'll do is open up the serial monitor. And it looks like it's already programming, because I guess it had some old code in there from before. But anyway, we'll give this a go and try uploading our code to the Arduino. See, there it's writing. That's good. And there it goes. So now it's programming. And it looks like that got everything in there. This is sort of weird that this last row is all Fs. Oh, it looks like actually maybe we're just reading too many, because 400 would be 1024. And so this would be 1025, 1026. So we're reading past where we want to. So let's just see if we have an off by 1 error somewhere. Ah, yeah, here we go. So we're saying base less than or equal to length. I think we just want to say base less than length because we're passing in 1024. So we'll just re-upload and rerun that. Not that it really matters. It's just cosmetic, but it's nice to see everything working the way it should. Okay, and there we go. And so this is 1023, 3FF. But that looks good. So that's one EPROM. I'll pull that out and I'll stick in the next EPROM. This is where it's nice that these are both programmed the same. You could just pop the other one in and program it the exact same way. So I think I'll just reset this and it ought to rerun the programming code. Yep, and there it goes. And that should program the second EPROM the same. And there it goes. And now we've got them both programmed. So let's test it out and see if it still works. Pull that out, and then I'll pop both of these back in where they belong. Then I'll power it up, reset, and everything looks good. It's now just to test things out. What I'll do is put in a simple program that just counts by tens. Okay, so what I've done is just put in a simple program that does an add from address 15. I've got a 10 in address 15, so it adds 10, and then it will output the result, and then it will jump back to 0. So that's what we've got programmed in here. So let's reset and let her rip. And there it goes. It's counting by tens. So clearly we have not broken things too badly. And the reason I counted by tens is because then we should see the carry flag when it flips around past 255. So let's wait for that. 20, 30, 40, 50, and then the carry flag is set, and it keeps going. So that's a really strong indicator that this is working well, because if the carry flag is on and the computer continued to execute instructions properly, that means we must have the same instructions set up in the other parts of the EPROMs that are addressed when the carry flag is set. So now I'm pretty confident that we've got things working well at this point. Now, obviously, I could do a lot more testing right now, but I'm going to push on and add the conditional jump instructions. And the way I've set this up, hopefully it'll be fairly straightforward to add those conditional jump instructions. Because essentially what they are is they're exceptions to this copy, right? Because what we've done is we've just taken this template and we've copied it 4 times. So we're doing the same thing no matter what the flags are. But in these cases where the flags are different, then we can do something different by just sort of adding some exceptions here. So I'll show you what I mean. First, what I'm going to do is define some more constants just to kind of make things, again, just make the code a little bit more self-documenting. And the first constants I'll define are for the jump carry and jump 0, just mapping the mnemonic to the binary value for those instructions. And I'll actually spell out the full binary value here just because we've been looking at everything else in binary. Okay, now we've got those defined. And the reason I'm doing that is just kind of make things a little bit more straightforward when we define our exceptions. So we're going to add a couple opcodes here for our jump carry and our jump 0. So jump carry is going to be this 0111. And jump 0 is going to be this 1000 opcode. And so for jump carry and jump 0, in the case where the flags are all zeros, so here where it's 0, then basically all of the steps are zeros. So I'm going to leave it that way in the code here. So right now these are just all zeros. So they're essentially no ops. But where they're not going to be zeros is in these cases where the appropriate flag is a 1. And that's where we have these exceptions. And so the way we can define those exceptions is after we made the copies of our templates here, we can add these exceptions. And so in this case here, for example, for jump carry, when the carry flag is 1, Basically, what we want to say is that for the carry flag is 1 on step 2, right? This is step 2 of jump carry. When the carry flag is 1, then we want this to be our control word, right? We want our instruction register out and jump. So what I can say here is I can say, after we've made that copy, I can say microcode. And so this is going to be flags where the 0 flag is 0, but the carry flag is 1. So in the case where the carry flag is 1, for that instruction, so the instruction in this case is going to be jump carry, and step 2. So in that particular case, then what I want the control word to look like is I want the control word to say instruction register out and jump, which is going to put the contents of the instruction register into the program counter. So this is just kind of our exception. So it says when the carry flag is 1 and we're on a jump carry instruction and we're at step 2, then this is the control word, and that just overrides what we would have here. So what we would have here is if our instruction is the jump carry instruction, that's here, and we're on step 2. So this is step 0, step 1. So step 2, currently we have nothing. And so normally we would want nothing, but in this one case where we have the carry flag set, then we actually want to do that jump. So that gives us a way to sort of easily have a sort of an override, I guess, for when a particular flag is set. We basically want to do the same thing for when the 0 flag is set. So when the 0 flag is set, 0 flag is set, carry flag is not set. On our jump 0 instruction on step 2, we want to do the same thing. We want to actually do the jump. So instruction register out and jump. And then for this last case here where the 0 flag is set and the carry flag is set, we also want to do our jump because we might have a case where we're doing a jump carry and the carry flag is set, but the 0 flag also happens to be set. So we want to do that. And then same thing here. If the 0 flag is set, we don't really care if the carry flag is set or not. This is 0 flag is set, carry flag is set for a jump carry. On step 2, we want to do a jump. And then 0 flag is set, carry flag is set for a jump 0 on step 2. We want to do a jump. And so I don't know, you may or may not like the way that I've written this, and that's totally fine. You can choose to do it your own way if you want to. But I think this is a fairly compact way of defining kind of a template for the sort of normal case where we don't care about the flags for each instruction. And then if we have an instruction where we do want to do something different for the different flags, then we have kind of a spot here where we can fairly clearly say what we want to do. So if the flags are in a particular condition and we're on a particular command, then on a particular step, we want to do this different thing that's different from our template. So I don't know. I think that makes sense to me. But again, with engineering, there's many ways you can do the same thing, and it depends what you're going for. I think, at least the way my brain works, this is a pretty clear way of defining these things. So, okay, let's reprogram our EEPROMs. So disconnect power here, pop these guys out, stick them in the programmer, and I'll go ahead and upload that. And it's programming the first EEPROM. And there it goes. And I could pick through this and try to find the particular exceptions and things that we programmed in there, but I'm feeling adventurous, so I'm just going to try it out and write a program that uses conditional jumps and see if it works. But first we'll program the second EEPROM here. Pop that in. And if I just hit the reset, that ought to reprogram that one. Okay, there we go. So let's pull that guy out, put it back in what looks like the right spot. And so now let's power that up and give it a try. Stop that, reset. Okay, that looks good, at least as an initial sanity check. Now I suppose we probably ought to write a program that uses a conditional jump. So I want to write a program that uses one of these conditional jump instructions. And so what I'm going to do is I'm just going to start with an output. So we'll output whatever's in the A register. And when we reset the computer, it's just going to output a 0. Then what we'll do is we'll add something to that. So we'll add 15, and I'll just put a 1 in address 15. So in address 15 here, I'll just put a 1. So we'll add 1. Then what I'm going to do is jump back to 0. So I'll say jump back to 0. So what this is going to do is it's just going to keep adding 1 and outputting the results. So it's just going to count. What I want to do is when it counts and it wraps around, so if I add this 1 and we get a carry, so I want to do a jump carry, then I want to jump down past this loop. So I want to count up until we wrap around, and then I want to do something else. So I'm going to do a jump carry. Let's see, this is going to be address 2, address 3, so address 4. I'm going to jump carry to address 4. Otherwise, I'm going to jump back. Because remember that if there isn't a carry from this addition, this jump carry is just going to be a no op. It's not going to do anything. So we're going to loop and add 15, output the results. We're just going to count up until we wrap around. When we wrap around, we're going to come down to instruction 4. And now what I'm going to do is I'm actually going to start subtracting. So I'm going to say subtract 15. So what I basically want to do is count up and then start counting down again. So I'll subtract 15 and then output that result. So it'll be at address 5. And then after I output that result, basically I want to keep looping in this subtract. So I'm going to loop around adding 1 and counting up. And then if we wrap around, then I want to jump down to address 4 and I want to create another loop down here that's going to loop around subtracting 1 each time until we get to 0. So now I can do a jump 0. And if we get to 0, then I will just want to go all the way back up to the top and start over again. So that'll be instruction 6. Instruction 7 will be, but if we haven't gotten to 0 yet, then I want to just continue in this loop where I'm subtracting. So I want to jump back to address 4. And so you can see I've created these 2 loops here, right? So there's this jump 0 that loops back to address 0. There's this jump 4 that loops back to address 4. And so there's these 2 loops where I'm just outputting and adding. And here I'm outputting and then subtracting, or subtracting and outputting. But then I have these conditional jumps. So if we have a carry from our addition, so we've maxed out our 8 bits, then I jump down here. And if we get to 0 and we're subtracting, then I jump back up here. So hopefully that makes sense. So basically, if this program works, then what we're going to do is we're just going to have it count up from 0 to 255, and then count down from 255 back to 0, and then count up again and just keep doing that. And so I think this will be a good way to test the jump carry and the jump 0 instructions and see if they work. And this is also a program that we couldn't have done before on the computer without a conditional jump instruction of some sort. Okay, so I'll go ahead and put this program in, and here's my cheat sheet so I can see what the binary is for each of those commands. Okay, so I think I've got that all programmed in, and just to show the conditional jumps, so we've got a jump carry at address 2, so let's go to address 2, make sure that one's right, and jump carry is 0111, so that's that, and this is 4, right? 1, 2, 4, so jump carry 4 in address 2, and then we have a jump 0 in address 6. Yeah, jump 0 is 1000, 1000, and we're jumping if 0 to address 0. It's confusing. And then there's the 0 there. So let's let her rip. Okay, and there it's counting very slowly. I'm going to speed up the clock here. And there it goes, counting up. And so hopefully when it gets past 255, we'll see the carry flag blink there, and we'll see it start to count down again. Almost there. And there we go. Now it's counting down. And so we're in this bottom loop where it's subtracting, outputting, and then if we get to 0, then it jumps to the top and starts adding again, but we haven't gotten to 0 yet, so it's just going to keep in this loop down here subtracting until it gets to 0. And we'll see the 0 flag flash, and now it's back in this top loop again. So it looks like our jump carry flag, or our jump carry instruction rather, and our jump 0 instruction are both working, or so it would seem. So that's exciting. What else can we do with it? Yeah, how about multiplication? You may recall that I mentioned in a previous video on Turing completeness that a conditional jump instruction was the key to being able to compute anything, and that certainly includes multiplication. Now, a few people found a clever workaround to doing multiplication without conditional jump using self-modifying code. And I think the first person to post about it was Matthew over on Patreon, where of course all my cleverest viewers hang out. And he also wrote a really good description of how it works, so I would definitely suggest checking that out. But if you do, you'll see that it outputs intermediate values before it gets to the solution, and there's also no way for it to do anything but halt once it's found the solution. So I don't know that it's a pure multiplication function, but it is extremely clever given the constraints of not having conditional jump instructions. And considering I said this, give it a try. Look at these instructions, see if you can write a program, but I don't think it's possible. I think it's pretty cool that a few of you proved me wrong, so thanks for teaching me something. But anyway, now that we've got some conditional jump instructions, let's look at writing a multiplication routine that doesn't have those side effects. The way I like to think about writing a more complex program is to start by writing pseudocode to come up with a general algorithm and then refine from there into the actual machine language. So if we want to write a program that multiplies two numbers, let's start with some variables. Now let's say x and y are the numbers that we want to multiply, and then product is going to be the result. So of course the challenge is our computer doesn't have a multiply instruction, but we've got an add instruction, and multiplication is really just repeated addition. So here's this algorithm that I came up with. And the bulk of it is this loop. And the goal is to go through this loop x times. At the beginning, we start with product equal to 0. And then each time through the loop, we add y to the product. And also to make sure we go through the loop exactly x times, we subtract 1 from x each time through, and then stop the loop once x hits 0. So in other words, if product starts as 0, and we add y to it x times, then product is going to end up equaling x times y. And then we can just output the answer down here at the bottom. So that's all well and good, but how do we actually do this loop until x is 0 thing? Well, we've got a jump 0 instruction, which seems like it might help. But remember that our conditional jump instructions depend on the flags that are set only after an addition or subtraction. So if we want to check whether x is 0, we've got to do it after an addition or subtraction from x. And right now, the only arithmetic we're doing with x is right here, this subtract 1. Okay, so fair enough. What if we do a jump if 0 right after the subtract command here, and jump down to the bottom where we output our product, and then we're done with our loop? Well, maybe you see the problem with that. We'd have an off by 1 error because we want to check if x is 0 before we subtract 1, not after. So there's a couple things we could do. One is we could put an add 0 right here that wouldn't change x, but it would update the flags register. Then we could do a jump of 0 based on the original value of x before the subtract. So that's one thing we could do. It would take an extra instruction, but that's not the craziest thing in the world. The Intel x86 processors had a compare instruction that was designed to set the flags before doing a conditional jump. Basically, the compare instruction does a subtraction and then throws away the result, but it updates the flags. So you can see here it says the comparison is performed by subtracting the second operand from the first operand and setting the status flags in the same manner as the subtract instruction. So I bet if you've been following along with this series of videos, you could probably figure out how to implement a compare instruction like that on our computer. So that's an option if we want to use the jump 0 instruction. But as I mentioned in my video on Turing completeness, in order for a computer to be Turing complete, we only really need one type of conditional jump instruction. So that suggests that it's possible to do this with a jump carry instruction somehow. And it turns out that it works out quite nicely. So let's think about what happens with the carry bit when we subtract 1. So we actually negate the 1 to get -1, and then really what we do is add -1 to x in this case. So what does -1 look like in binary? Well, if you're not sure how -1 is represented in binary, you might want to check out my video on negative numbers in binary, because it turns out -1 is represented in binary as all ones. So in other words, it's the same as 255. So actually subtracting 1 from x is exactly the same as adding 255 to x. And again, if that doesn't make sense, check out that video on negative numbers in binary. So what happens to the carry bit when you add 255 to something? Well, the carry bit's going to get set anytime the result of an addition overflows. So that is if it's more than 255. Well, that's going to happen if you add 255 to anything. Or, well, anything except 0. So think about that for a second. After we subtract 1 here, the carry bit will always be set unless x was 0 before the subtract. So bingo. A jump on carry after the subtract will know whether x was 0 at the beginning of the loop or not. So it goes to show that it's possible to write this using either jump 0 or jump carry. So now I can rewrite this pseudocode to be a little bit closer to what we would program the computer with. Although I'm still using variables and I'm using labels to sort of suggest where we're jumping to rather than filling in all the addresses just yet. But now we've got the jump carry instruction here, like I talked about, and we can walk through this to see if it makes sense. So let's say we're multiplying 3 times 5. So x would be 3, y will be 5, and product is going to start out at 0. So we start by loading x, which is 3, subtract 1 from it. And when we do that, the carry bit will be set, because when we subtract 1 from anything but 0, the carry bit will be set. So the jump carry, it jumps down to continue here. Then we store x, which is now 2, load the product, add 5 to it, and then store that. Then we go back to the top. Next time through is the same. X is 2, we subtract 1 from it, the carry bit will be set. So we continue down here, update x, which is now 1, and add 5 to product and store that. So now product is 10. Then we go back to the top. Now x is 1, we subtract 1. Again, the carry bit is set, so we continue down here. We store x, which is now 0, add another 5 to product, so now product is 15, and then we go back to the top. This time, though, we subtract 1 from x, which was 0, but when we subtract 1 from 0, the carry bit isn't set. So this time we drop into this code here. And here we load up the product, which is 15, output it to the display, and then halt. And there we go. We multiplied 3 times 5. And of course, we could do other things here other than instead of halting. So unlike that clever workaround that a few of you came up with here, we could theoretically jump somewhere else. We could execute more code or continue on with our program. So finally, to take this to the next step, this is what the completed code would look like for this program. And really all I've done is substitute in actual memory locations for the variables. So instead of saying load a x, now I'm saying load a 14. And 14 is the address where our x value is going to be. And here where I said subtract 1, Well, the way the subtract instruction works is it subtracts a value from memory. So now we've got subtract 12, and then we've got a 1 sitting in memory address 12 here. And then instead of jumping to labels like continue or top, I just filled in the actual addresses. So the jump carry 6 or jump 0. So this is what we'd actually need to program into the computer. And if I convert all those instructions to binary, these are the actual ones and zeros I've got to toggle into the dip switches. And of course, we'll just need to fill in the x and y value to whatever numbers we want to multiply. All right, well, let's see if this thing actually works. I'm going to go ahead and program this thing in. So I'll just go through each address one by one and put in the binary machine code for each instruction. And I'm sure I'll speed all this up so you don't have to watch me do it in real time. All right, so everything's in, but we still need to initialize our product, x and y values. And so I've already got 0 put in for the product. And so then x and y are going to be the two numbers that we want to multiply. So if we want to do that same example of 3 times 5, then we could put that in. So in address 14, we'll put the 3. So that's the 3 in address 14. And then address 15, we'll put 5. And so that'll be 3 times 5. And then the product is going to be put in address 13. And that's initialized with 0, which is where we want it to start. So let's give this thing a try. If we go back into run mode, we're already reset. If I start the clock, this ought to run the whole thing and output the result of 3 times 5 on our output and then halt. So let's give it a whirl. Hey, and there it goes, 15. And it halted. So that looks like it's working perfectly. So now if we want, we can try multiplying two different numbers, maybe give it a little bit of a harder problem. And so again, we've got to initialize our variables. So our product now has got a 15 in it, right? Because we just ran the program and got 15. So we need to initialize that back to 0 before we start. And then x and y, of course, are going to be the two numbers that we want to multiply. So let's make x 7 and y will make 8. 7 times 8 is a nice hard multiplication problem, right? And so we'll go back into run mode, reset, and start the clock, and we should get 7 times 8. 56, I think that's right. And so there we go. We've implemented enough of an instruction set to be Turing complete. Now with only 16 bytes of RAM, the computer is still pretty limited, but I'm really curious to see what programs you all can devise for it. The most interesting program I've been able to come up with in 16 bytes is this program that computes Fibonacci numbers. And you can check out one of my older videos where I walk through how it works. But I also know a number of people have expanded the memory to 256 bytes or even 64K. I'm really excited to see what programs people can run on those machines. And maybe in a future video, it'd be fun to feature some things that different people have come up with. So if you'd like to see that, and if you've enjoyed my videos in general, consider clicking the subscribe button and also clicking that notification bell so that you'll find out about future videos. And if you want, you can even support these videos directly over on Patreon. And I really want to thank my patrons there whose contributions are truly helping me make more content like this. So on behalf of all my viewers, thank you very much for helping make this possible.